Good afternoon, this is Schweitzer, and we're looking to continue our thoughts on equilibrium. Today we're going to review a couple of things here, and then introduce a few small things before we try a few things out here. Now, equilibrium is where we have a reaction that goes both towards reactants and towards products. We mentioned yesterday that K value is just simply some sort of a fractional number representing the concentration of products divided by the concentration of reactants. Occasionally I use a little dial that says, okay, we have the concentrations of my reactants, concentrations of my products, and at this point I have a dial that's showing where I am when I reach my stalemate or my equilibrium. Now I'm showing this as a way of calculating, but previously we've already shown that a reaction that this follows a unique little algorithm as far as how you calculate it. So if we have a K value which has more product, the K value should be greater than 1. If the K is right in the middle, then the K should equal 1. And if it's over here someplace, then the K should be less than 1. Quite often, again, kids lose track of what K really means. So a kid, for example, said, well, what does K mean? So I asked the kid, okay, well, how old are you? And the kid says, okay, Mr. Kid says, okay, I am 15. Well, at this point, what does 15 mean? Well, it means, he says, well, it's how old I am. Well, really, 15 is just a number on a scale from 0 to however long you've been living. Maybe you think 80 or 100. And you're like right here on that scale. So we could also make the same scale like this and say, okay, well, everybody is born and everybody is at some point going to expire. And we don't always know when you're going to die, but at some point you might say, well, if I'm 15, I'm like right here. Okay? This is where I currently am. Now, new idea here, okay, is where you currently are versus, let's say, the end point. K is where you end. But what about where you currently are? We call where we currently are as being Q. Okay. Now, Q is a short-term little letter standing for reaction quotient. And I often refer to Q is where you are, K is where you're going. They're both calculated exactly the same. It is the product concentrations multiplied by the powers divided by the reactant concentrations. Okay. We'll deal with that a little bit as we move along here today. And then the last thing we'll do is again reviewing. Yesterday we added in Kc, which means we are measuring these. So how do we actually get this guy? What is the actual calculation? Kc measures everything is in molarity. Things that don't have a molarity we cannot use. So we cannot use the solids, we cannot use the liquids. We can use aqueous, we can use gases. We talked about Kp. Alright, this is where everything is measured in partial pressures of atmospheres. The things we can use are simply gases, and that's it. We cannot use, well, solids, liquids, aqueous, so pretty limited. It's possible that we wouldn't even have a Kc value. Alright, so it is possible that we don't even have a Kc value. One unique option of our chemical reaction is that of dissolving. This is an example of an equilibrium process. If you take and you add in, say, AgS, silver sulfide, it will dissolve in water and form Ag plus 1 ions, this is aqueous, and S minus 2 ions, aqueous. Let's draw a picture of this, draw it in. we'll get Ag solid on the bottom. Then this stuff starts to dissolve, but eventually it reaches a static point, and the sulfur is all everything's dissolved there, where it can no longer continue just to dissolve and dissolve and dissolve. And then we get a reverse process that eventually will match it, and we go to what's called equilibrium. For this reaction, okay, we'll have a unique little lettering underneath the K value called SP. It actually stands for solubility product. Now, again, we could just call it KC and not worry about it. So the SP doesn't change anything that we would normally do. It's still measured in molarity. It's just giving you a little pointer and said, by the way, this is the type of reaction that we're doing. We're doing a solubility reaction. So we just call it that, KSP. And if I were to follow my rules, two aqueous compounds, this one have a 2 in front of it. I would go bracket Ag plus, bracket, squared, S minus 2, bracket, and then there would be nothing on the bottom because this is a solid. Alright, let's flip to this next page. Now, your page may not look exactly like this, but when I pasted it, it looks a little different. And things are constantly changing, so let's just kind of work through this. Alright, so we have a reaction here now. I've added in here your K value and your Q value. Q is where you are, K is where you're going. So this is the start, and it looks to me like we have lots of reactant and not so much product. In the end, though, we're gonna be equal. So I'm gonna have my equilibrium starting right here. So I just have to make sure that at K, this represents my K value, and this represents my Q value. At that point, just increase there, and decrease here. Keep in mind, you cannot gain product without losing reactant. Stoichiometrically has to hold true. Alright, next one on our sheet here. Okay, so now we're here, equal amounts. I want to go to a reactant favored. Okay, so I'm going to start out with them both equal, and I'm going to have concentration of R, concentration of P. But at equilibrium, I want there to be more R, less P. These quantities are not just qualitative at this point. So the R is going to be gaining R, and leveling off, and then P like that. Okay, try another one. Alright, now here I have two different starting points, so we'll do this guy is Q, let's do Q1, and this guy Q2. Alright, so let's do the first one. The first one, we're ending in the same spot here, and you could even do them on the same graph if you'd like. But lots of reactant going to lots of more product. So I'll start out here with lots of reactant, very little product. In the end, I want there to be lots of product and not so much reactant. So this guy will just drop to here, and this guy will pick up to there. And in the other one, now this is one thing about, I mentioned the example of age. You can start out young and you can end up dying, but the whole idea of going from old to young isn't really all that realistic. So, but in chemistry, we can go both ways. So here we have lots of product, and we're going to actually go backwards to attain our equilibrium. So I'll go here, lots of product, and little to no reactant. And I want to end up in the same spot I was before. So you could literally say, okay, I want my product to be right here, my reactant to be right here. But in this case, I'm just going to do this and this. Alright, keep in mind the amount that you gain and lose has to work somewhat with the stoichiometry of what this is happening. So far, all 1-to-1-to-1 ratios. Alright, so let's look at this last guy here. Use the chart here to indicate on the graph, so I'm going to draw on this graph both a Q and a K. So the Q says we have lots of A, not so much B. And again, in this situation, A is the reactant. So we'll start out right here. This is our Q. That's where we're currently located. And I have lots of Q, lots of R, almost no P. No product, no B. Ending up in the situation where, okay, we have it, still lots of A, not so much B. And right there, this is my K. Reactant still is being favored. And we will stop there for today. Thank you very much.